Hello, everybody. Welcome to Dive into AI. This is session 1, Introducing AI and Building Bridges. My name is Shen Malloy, and I will be your host for today. I would also like to introduce my fellow workshop organizers at Zeus Atlantic. So we have Shayla Fitzsimmons, Executive Director, Alexi Bachardax-Westcott, who is the Engagement Specialist, Alex Johnson, our AI Training Lead, Jay Kumar, who is our AI Developer, and on the panel, we also have Chris Whidden, who will be speaking about his expertise later on in the session. I would first like to begin by acknowledging and respecting the First Nations, Métis, and Inuit peoples on whose traditional territories Zeus work is conducted across Canada. We strive for respectful relationships with all Indigenous peoples as we search for collective healing, true reconciliation, and honoring these beautiful lands and seas together. I am coming to you from Kipucha, otherwise known as Halifax, the traditional unceded territory of the Mi'kmaq. Now, before we get started here, I do have a couple housekeeping items to highlight. We will be monitoring both the Q&A and the chat box today. You are welcome to use the Q&A to ask questions to the panelists and to chat with the other attendees. This workshop will be presented in English. Zoom does offer live captions and automatic translation features that you have the option of turning on or off in the control panel. You can set the caption and translation language to that of your choosing. Please note that this session is being recorded and will be shared through our social media channels and on our website to be used as a public resource. If you have any questions at all about the session or are experiencing any technical difficulties, please connect with us over chat, or you can send a quick email to info@zeusatlantic.ca. Now we will start off with a little interactive activity here. Thank you to everybody who completed the pre-workshop survey. To open this webinar series, we would like to share a quick Mentimeter poll with you to learn about who you are and your experiences with AI. So to access the poll, you can open up the Mentimeter Zoom app when prompted, or alternatively, if your Zoom is being a little finicky, you can also go to mentimeter.com and enter the code that you see here on your screen. So I'll just get 1 second to get that poll set up for you. So you should see the Shayla Fitzsimmons is inviting you to a Zoom app pop-up open, or to mentimeter.com, and the code is there at the top of the screen. So the first question, where are you joining from us today? There should be a little interactive icon that you can click and drag and place to wherever you are. Again, let us know if you're experiencing any technical difficulties, but it looks like most people have it figured out. There should be a little icon right around Hudson's Bay where you can just click and drag to wherever you are located. Okay, I think we are good to move on. The next question that we have for you, what sector do you work in? There should be, this is just be a multiple choice answer. You can pick multiple if that applies to you, but we'll just give you another minute to answer this one. Well, it looks like some people are having issues with the slide changing on the Zoom app. So I would recommend try going to mentimeter.com and entering the code there. Okay, so people are saying it's the same issue on the website. Apologies for that. Let's try troubleshooting our end, Shayla. But also, if you would like, oh, there we go. We see, okay, it's working now. Ugh, crisis averted. No worries, guys. But also, I was just about to say, if alternatively you would like to introduce yourself in the chat, that is absolutely welcome as well. But answers are flying in now, so I think we're good to go. All right, hopefully let's change the slide, see if the poll continues to go in our favor. Looks like we have a lot of people from nonprofits here, which is great. Now, this question needs a little bit of explaining. So recently, there's been a viral moment with some AIs where if you ask different language models, such as ChatGPT, they have different answers for how many R's are in the word strawberry, just based off of different ways of processing information. So just as a little food for thought, fun question, I would like to ask you, a human, how many R's are in the word strawberry? I promise it's not a quick trick question. Obviously, there's 5 R's in the word strawberry. Anyway, just a fun food for thought question that maybe not all AI is properly trained, let's say, but something we'll dive into definitely later. This is just a little example of what happens when you ask ChatGPT how many R's are in the word strawberry. And it will never give you a straight answer. All right, now back to questions about you. How would you describe your level of AI proficiency on a scale of I'm just dipping my toes in, I've never really considered it, to I am an expert, call me Elon Musk? So general consensus is that most people are in the beginning proficiencies, which is absolutely fantastic. This is what this webinar is for. And now we're going to look a little bit into what are your particular interests with AI. Maybe this is something to do with your job, what you work with. Maybe it's more of your personal interests and how you see AI in the future or want to know more about AI. And this could be something on the screen on your options. This could be something completely different. There is a wide breadth of AI knowledge to learn about. This is not a single answer. But it's great to see generally there's a wide range of interests in all areas of AI. Okay, now we are going to move on. This is the last question that we have for you before we dive into our presentations. Since the beginning of the year, how many papers do you think were published relating to aquatics and artificial intelligence? This is more of a trivia question than anything else. Just a general knowledge of how much literature do you think has been published in the last year, especially considering AI is such a new emerging topic. A little all over the place, generally towards the lower end. I don't know if I should give away the answer just yet. I would say this is probably skewed towards the couple hundreds, but I think the actual answer is 5,000, around there. So right in the middle. Okay, now we can move on to our final bonus question here. Okay. This is a fill in the blank for you all. When you think about AI, what are some of the things that come to mind? Maybe some keywords, some terms of reference. There are no wrong answers. All right. Amazing. Future efficiency, a lot of automation, data. Wow, I can't even keep up with the cloud bubble happening. Okay. Well, thank you so much for participating in that little interactive get to know you at the beginning here, just to give us a sense of who you are, where you're coming from, and your comfortability with AI and with ocean data. So now we are going to get into the thick of our presentations. Let's just close down the poll here for 1 second and switch back to our main slide deck. The first of our speakers today. I would like to invite Alexi Bakardas-Westcott to give an introduction to sea use and building bridges.
Hi. Hello, everyone. Thanks for joining us today. My name is Alexi Bakardas-Westcott. I'm engagement specialist with Zeus Atlantic, and I'd like to give you a presentation today that will give you a little bit more information about Zeus, who we are and what we do, and also specifically our Building Bridges project. And hope that if you have any questions at the end, that we might be able to help answer them. Probably move to the next slide there. So we'll start with about Zeus. And I think you can move to the next slide there. So we'll start with Zeus. Our vision is as Canada's nucleus for ocean observing, Zeus makes connections for a sustainable future. And then we can move to the mission is to foster partnerships and grow powerful online platforms that generate information, knowledge, and place-based solutions to advance our understanding of the ocean. So to place Zeus within the global system, ocean observing systems around the world are bringing light to the sea of data that was previously obscured from those not directly involved in research. And now Zeus joins an international framework to contribute its data to the international effort that continues to gain speed. Canada's ocean of data fills vital gaps in global observations through our work at higher latitudes and enduring time series. Our contributions are important to an ocean observing system future where fair data are widely available and well utilized for sustainable ocean health and economic growth. So we can go to the next slide. We can see our guiding principles. And I just want to let you know that for value proposition, Zeus seeks to improve access and visibility to high quality observational and model ocean data and information, increase collaboration and coordination in the ocean observing community, increase national coordination while remaining regionally focused, and contribute to evidence-based decision-making in the ocean domain. We can go to the next slide. And the next one. So collaboration within Zeus is that we work across the country and across sectors to unite the knowledge, expertise, and digital infrastructure of Canada's ocean observing community, working with ocean data for our ocean future. And primarily our primary partners are the three regional associations, Zeus Pacific, the St. Lawrence Global Observatory, and Zeus Atlantic. So if we talk a little bit about the role of the regional associations, we can move to the next slide. Regional associations engage and work with regional data contributors and users to foster participation in Zeus. So if we look at the graphic there, we can see that the regional associations work together and independently through regional outreach and data integration. We pay specific attention to compliance to national standards, and through working together, we allow for national and international data visibility. And we'll move forward again to how Zeus works. Oh no, I skipped one of my notes. So what does Zeus entail? What do we provide? What type of data will you find with Zeus? So we have our essential ocean variables. And you can see that they include there's more than what's on the screen here, but we have categories of biology and ecosystems, physical, biogeochemical, and cross-disciplinary. And Zeus is currently accepting all global ocean observing system variables. And now we can move to how Zeus works. So through a lot of moving parts, data from partners in many sectors share data with CUs through web services or in direct transfer. CUs integrates and hosts data and metadata made available through open access and visualization tools. There is power in numbers with access to data from multiple sources. Those accessing data through CUs may be using it to further validate your own data or models, and also to help you see the bigger picture. And we can move forward. So one part of how, to the next slide, please. One part of how we do that is one of the tools that we have is the CU's metadata entry tool, which aids in the data submission process. CU staff in each region work with data providers to complete the form as part of integrating their data. And we can move to the next one. So I'm just kind of whizzing through CUs in general. So at some point we might have a few questions about this. I just need a drink here. So data exploration tools for CUs include the Data Explorer, which allows users to search geographically across data sets. The Asset Map, which allows users to search geographically. And the Data Catalog, which lets you search by keyword and refine your search using the metadata. So we can move to the next one. The Data Explorer lets you search geographically across supported data sets. So you can see in the image here, you can see the data points on the map. And the data points on the map are including multiple different data sets based on your search criteria and what you want to see up there. And so you're able to filter, aggregate, and download just the data that you're looking for. And you're able to download the data in a standardized CSV format, as long as the data sets that you're looking to download are less than 1 gigabyte. And we can move forward. The CU's data catalog allows you to use filters and keywords to search the full collection in CUs of data sets across Canada, and to find data or metadata in its original format. And many of the data sets can be converted to a format that meets your needs when you're trying to then download it for your own use. And the last one, if we can move to the next one, this CU's catalog map allows to search data sets filtering by EOVs, the essential ocean variables, and by viewing the data set location on the map. And the final tool that I wanted to talk about is ERDAP, which is a data server that provides a simple, consistent method to download subsets of scientific data sets in a common file format and to create graph and maps. So this is our primary way of accessing the data in CUs if you aren't using the Data Explorer. And if you're new to ERDAP, we have a training video to help you along the way in learning how to use it, and you can find it on our YouTube page. So now I want to shift gears and talk about building bridges, which is a new project that we just started this year within CUs. So the longer title is Building Bridges, Artificial Intelligence Use in the Ocean Sector. So this is a project approach to accelerating the adoption of artificial intelligence, or AI, in the ocean sector, with a focus on connecting not-for-profit organizations with the tools and information necessary to understand and implement the opportunities offered by AI. Through collaboration of 4 national academic and not-for-profit partners across Canada, Building Bridges aims to address multiple components of the high-level artificial intelligence pipeline, which begins with having the knowledge and skills to identify and develop solutions for scientific questions or problems which may be resolved with artificial intelligence. So we have a few, pillars of or large areas of focus within the project. And one is engagement, community, and workshops. So to accomplish what the goals within the project, and this is something that we've been working on the past few months, we've been working on engaging, talking to people and organizations to see what they think works, what isn't working, what the gaps and the needs and opportunities are, what challenges people have, what makes it easier for you to work with AI, or what has it made it harder. And based on this understanding and needs assessment, we have some activities planned. And one is this first workshop, which we have been aiming to use to bring together the ocean community and understand what the opportunities are with AI in Canada and the oceans. We aim to help people connect and provide a forum so that people can share best practices and knowledge and further advocate, further advance AI in the ocean sector. The next two workshops that we have, which will be coming up in 2025, will probably be more focused depending on where we are seeing the biggest areas of interest arise. And if anyone has more feedback about the types of questions I just mentioned, definitely reach out to us. And also maybe you'll be hearing from us as we continue on that first step of understanding what the needs are as we continue to develop our plans for the upcoming workshops and training. So the next slide, please. Another area of focus is training. So we'll be creating training materials to help address the gaps and the challenges that we identified during the requirement analysis. So we'll be looking for what information or skills are most needed by not-for-profit organizations in the ocean sector to take advantage of AI, and working to create free online materials that will be made available through websites such as Udemy, that people can access and take advantage of to learn about the opportunities available with AI. The training materials will be developed to address the needs and gaps that currently exist in the ocean sector with regard to AI. As part of the training materials, we will also be planning to offer case studies so that which include analysis of specific applications of AI in the ocean sector and the associated benefits. These will be both for information and also tools for learning in conjunction with the online training materials. And the last is a primer focused on AI governance, which is a set of methods and frameworks which organizations use to manage their use of AI. It is the methodologies that you would employ to ensure that your model works as intended, minimizes the costs and the risks, and ensures the model is explainable, transparent, and ethical. So the next area is that acquisition and integration. Because data is such an important part of an AI model, you need a fair amount of data to start building your model, and you need to ensure that your data is accurate, because if you put bad data in, you will get bad data back out most likely. We will be working on developing a data cleaning tool to help with QA and QC of data. There will be some work done for annotating data sets so that they can be used for AI models for training and validation. Persistent identifiers and knowledge graphs for data sets within CEUS will be investigated as a means of helping people find related data sets that would also be useful in an AI model. And finally, integration of data itself into the larger CEUS system so that you can come to CEUS and find the data that you need to train and validate and run your AI model. Finally, as part of building bridges, model development and model deployment is included. We'll be working on a few different AI models as part of the project, all of which will ultimately be open source. One is AI for data management to help streamline the process of actually managing data, which can be quite time consuming. One is an AI model to map mussels using drone footage, and another is a model to identify anomalies in hydrophone data. And finally, a data reconstruction model, which uses AI to look at the gaps in models. And so it was a bit of a quick overview, and just to let you know that today and in the next 2 sessions, we'll have little bits of information about building bridges and what we're working on and planning, and also what some of the results that we already have as part of some of the talks that will be coming in, especially the building bridges lightning talks. We have 2 coming up later in the session. So in conclusion, building bridges is an approach to increasing the adoption of AI with a particular focus on the not-for-profit sector, with a holistic approach to the AI model pipeline, including everything from opportunity identification to deploying an AI model. And within the project, we want to develop the tools, the applications, and help with the resources that are needed so that organizations can take advantage of the opportunities and value that is provided with AI.
All right, thank you so much, Alexi. We will now move on to our plenary presentation. Chris Whitten is an assistant professor in the Faculty of Computer Science at Dalhousie. He has expertise in algorithm development, data science, machine learning, and optimization, with a focus on bioinformatics and ocean research. Chris is particularly interested in practical, collaborative, applied research with ocean scientists and industry partners to help translate AI technology research and development to practical and responsible uses. He is an editor for the International Council for Exploration of the Seas Journal of Marine Science, principal investigator of the Meridian Ocean Acoustics and Ship Tracking Research Initiative, and the lead researcher of Dalhousie's transformational Canada First Research Excellence Fund grant to transform climate action through ocean study and impact. Whew. I will now pass the mic to Chris.
Thank you. To clarify, I'm the lead of the AI sub-piece of Transforming Climate Action, not the whole thing. It's a huge project. But thanks, everyone. So I'm here to introduce what is AI and how can you apply it for ocean applications. Next slide, please. So we're all here because we're interested in artificial intelligence. I probably don't need to say this, but it's becoming one of the most important tools that you can use. And so the question to ask is, how can ocean researchers, those in the ocean industry, not-for-profits, and so on, leverage these tools? And what do they mean anyway? Next slide, please. So to start, we need to take a step back and say, well, what is artificial intelligence? What does that even mean? Next slide, please. So one definition that is fairly simple, but covers quite a bit of what AI is just that they're computer systems that can learn. I'll go into a bit more detail in the next few slides. So next slide, please. So kind of the difference between AI or older term you might have heard of machine learning and standard software is you program standard software to apply a set of steps. That doesn't mean it always does the same thing. It can have varied behavior based on user input or based on randomization or so on. But you're writing a piece of software. That software itself has a purpose and doesn't change. With AI, it means that we are taking in some sort of data or problem we're trying to solve, and we are modifying an AI model to solve that problem or fit that purpose. Next slide, please. So machine learning, that older term, means that you have some sort of input, some problem trying to solve, like you want to say, is it a picture of a cat or a dog? You train a model. At first, it doesn't work very well, get things wrong most of the time. As you give it more and more training examples, input and output examples, the input you have and the output you wish it had, it starts to modify that model to make it more likely to get that result that you want. At the end, you have a model, you can apply input of the form that you're giving it with whatever assumptions that has and get some sort of output out of that. Next slide, please. Lately, you might have heard of something called deep learning. Deep learning really means machine learning with more data and a much bigger model. AI models kind of hit a point of diminishing returns back in the 90s where it seemed like they were going to take off and they really didn't. Really the big advantage with deep learning was, okay, now we have faster computer systems, more memory. We can use things like graphics processors and throw a lot of data to build really, really large models. And then surprise was that these actually started to work really well and generalize to non-obvious purposes. Next slide, please. Even more recently, you might have heard the term generative AI. This is sort of a catch-all term for AI that creates something, like ChatGPT, where you ask it a question and get an answer. Here, again, it's a form of deep learning where you are providing a lot of input, training a large model, but now you're giving it so much input and input of different forms so that you can get different uses out of it from that same interface. So I mean by generative AI. Next slide, please. So you've heard about all of these different things. This one's, you can just start stepping through. Why do we care about AI? We've got all these different kinds of models. Well, it's for an organization to get increased or new revenue, to improve the customer experience, to reduce your business costs, to improve accuracy over some sort of baseline. A big one is automation of manual tasks, reducing human error or standardizing something and normalizing it so you get the same use out of it each time, or allowing people to do more. So reallocating skill resources to the thornier problems rather than the common tasks that take a lot of time and effort. As I saw in that Mentimeter poll at the beginning of this session, a lot of people are here for some of these things. That's what you think of when you hear AI. Great, that's why we're here. Next slide, please. And decision making. How does AI do this? Or what are some examples of AI? I mentioned maybe we want to show a bunch of pictures and say, is this a cat versus a dog? Or given a picture, identify here in this picture, this is where the cat is. We call these tasks things like on the upper left, classification localization, where you're actually finding where it is, object detection, a more generalized task where you have multiple different objects and you're not just saying find just the cats, find everything in this image. Or maybe instead of drawing boxes around your objects of interest, you want to get the exact shadow or outline, so we call segmentation. So this is one kind of AI task. In the upper right, you might have heard of something called AlphaFold, where the goal is, given that you have a DNA sequence, can you predict the 3D structure that it will fold into? And so AlphaFold is a way to do that with AI. Lower left, things like GitHub Copilot or ChatGPT or other aspects of coding, where you can actually use these tools now to write code for you when you describe what that code should look like. In the lower right, something you might or might not think of as AI is more statistical kinds of analysis, like classifying something into multiple different sets, or regression, like linear regression or more complex techniques, where you're trying to identify some sort of a number value, like predicting how ocean observing variables are going to change in the future, like will we have low oxygen events in aquaculture pens. Next slide, please. So those ones were all sort of standard AI things you might or might not have seen before. How do we actually get these out of AI? How does a computer say this picture is a cat, this picture is a dog, or this is the box around the cat in this image? It's a lot of math. We have some sort of an input. We turn that input into some sort of numbers, like this picture in the upper left. Look at these as matrices of values, have a lot of so-called layers, which are other kinds of matrices of values that are transformed in various ways, like multiplication, convolution, and so on. At the end, we get some sort of output layer, turn that into a number. So that's what we mean by AI. We mean sequences of mathematical operations that transform the input into some expected output. YOLO is a common technique for you only look once for identifying objects fairly quickly. In the upper right, we have a generative adversarial network. That's an older technique for generating images of various types, where you combine a network that creates an image and a network that says this is a real or a fake image. Both of these learn together to transform the output. You might have heard of things like Stable Diffusion. We'll talk about it in a minute. It's a similar kind of AI, but it works differently. For natural language processing, we read in a bunch of documents, text, web pages, books. We transform this into some sort of a representation of that text and embedding. We throw it through the machine learning model. We get a common sort of representation of that, and we train different parts of AI to do things like say, here are all the nouns in this phrase, or answer questions, or other kinds of natural language tasks. Again, on the side of older style AI, statistical analysis, we can have things like random forest or linear regression. Random forest is a bunch of different classifiers that create decision trees. You put these together and take the most common output or apply things to average the outputs to get values out of those. Next slide, please. So those are some sort of common classes of AI. There's also much bigger, larger scale AI systems that are being built for things like climate analysis or ocean observing. So a newer one from Google DeepMind called GraphCast applies AI to predict all of the weather across the entire world 10 days in advance. A lot of the novelty here is the reason this works is they're taking a full map of the Earth, applying subscale analysis, and then they're sort of using that to predict what's going to happen next, what's going to happen next, what's happen next. Kind of like ChatGPT with words, but now for weather prediction. Next slide, please. And then I mentioned Stable Diffusion. You might have heard of this, where you just type in what you want to create a picture of, and then it creates it, or Midjourney or other sorts of these tools. These work by combining multiple different AI models, where you take your text, and like we saw in the NLP kind of technique, you turn that into a representation, and we have our images, put that into a shared representation, and by having these paired values, we get a mapping of sort of concepts of text to pictures. Now it learns based on these concepts and uses that. So when you create some new novel text, to find something in that representation space you've created that maps to an image. So that's what we mean by these sorts of diffusion-based models. They start by getting something that's a fuzzy picture, making it more and more concrete by going through this sort of an idea of what does a set of text mean in terms of images. Next slide, please. So I've shown you these models. I've told you what they can do. You've all seen examples of this. How do they actually work? How do computer systems learn? Most of this boils down to data, some sort of a model you've created for a particular task or a larger scale kind of set of tasks, and then having your labeled or unlabeled training outputs and making the system work more closely to match those input-output examples. So next slide, please. This is what I mean by AI in practice. The first step, and was kind of alluded to in the previous presentation, is really just modeling that data. Data is key in artificial intelligence, just like any analysis. This could be images, text, video, as I said, DNA sequences, weather, could be movie preferences if you are Netflix and you're recommending what to watch next. All these different kinds of data need to be turned into numbers into some sort of AI system. One example here, if you're trying to classify different kinds of pets, you could have cats, dogs, turtles, fish, or other things. Could be more granular labels. One way to do this is by assigning a vector of numbers and saying if you have a 1 in the first position, it's a cat. A 1 in the second position, it's a dog. Third position, it's a turtle. Fourth, it's a fish. This is a way of getting categorical data, like classes of animals or pets or other kinds of things, could be fish species, for example, into a machine-readable numerical format. But this is the first step. You need to do this to have AI. Next slide, please. Then we need to do those other steps, create that AI model. These are different mathematical operations, like in this example shown here, where we take a portion of this matrix of values, this table of numbers, representing, for example, an image or some text or something. And then we want to take information and modify it in different ways to give potential for that AI to learn something about parts of those numbers. In this case, one of the most common operations is called a convolution. If you're familiar with things like fast Fourier transform or other kinds of analysis of sort of signal processing kinds of analysis, it's a similar thing. It's like a multiplication in that space. We take a subset of the numbers and then turn those into one new number, and we are reducing the size of our matrix of values. We can apply these multiple different times, and that is sort of squeezing the data down to a smaller space, where if you are squeezing data down to a smaller space and getting out to an output, the idea is that it sort of forces the machine to learn what are important parts of this that need to be known. It's kind of like a compression technique can turn into an analysis technique. Next slide, please. I'm not going into details at all, but this whole process of learning uses something called backpropagation, where you take the input, feed it through to the output, and then you say, what if? What would I need to do to modify this model to get the desired output? If you give a picture of a cat and it says the dog, you say, what made that decision? What parts of this in these numbers were weighted highly, so they were given more preference, that led to this being called a dog instead of a cat? And which ones were weighted low, that if you increase their weights would be more likely to make it be to say this is a cat versus a dog? Then we apply some math. We use some calculus and differentiation here to say, here's the optimal way to modify these numbers, so you're more likely to get the right answer next time. This is the heart of machine learning or artificial intelligence. It's modifying this model where you're putting sequences of numbers through different kinds of mathematical operations, modifying the weights of those mathematical operations, say multiply this number by a 2, this number by a 10, this number by a 5. And if this 10 is too high, reduce it to a 9. If this 2 is too low, increase it to a 4. And you're putting more or less weight on the parts of this AI model that are more likely to lead to the answers you want to get. This is why it takes a lot of data to learn something and to generalize it. It's also why if you give it something that is very different than it's seen before, you often get the wrong answer. All you can get is what you've trained into this model based on what it's seen before. Next slide, please. So that said, when we actually create AI models and we're doing AI work, we don't spend a lot of time working on that part of it, that part of model design. There's a lot of standard kinds of tools, or you can modify them a little bit. Really, it's mostly about the data. If we take in something like ocean observing data, we're going to have issues like wrong measurements, missing values, biofouling on our sensors. If we're taking in things like ship manifests, might be hand-entered mistakes. We could have our timestamps or time steps not aligned in our different sorts of data we're getting. If we're looking at images of cats and dogs, maybe one is 200 by 200 pixels, another is 500 by 500 pixels. We need ways to align those data. We can get shadows, occlusion, poor lighting, and so on. So most of AI analysis is cleaning the data and having a normalized workflow and pipeline that can get you to standardized data sets, kind of like what CUSE does for ocean observing variables. We do those same sorts of steps. Next slide, please. That said, you can do all this work, standardize and normalize your data, have it work very well. But if you have the wrong assumptions in the way you build this or in what kind of data you're going to see in the future, you can get wrong results. If we assume we have linear relationships and we do simple linear regression, but we actually have complex nonlinear relationships, we're going to get wrong answers. If we assume a normally distributed data, maybe things like lengths of fish, and assume it's a normal distribution, but actually in our data, what we get are a combination of really small and really long fish, you're going to tend to get values in the middle that you very rarely see. If we're looking at things like classification of species of fish or plankton or other kinds of marine life, typically you tend to have some of these are much more frequent than others, which skews the results you're going to get. Measurement frequency. So if we are trying to get weather predictions at the what's going to happen in the next 10 seconds, but we get values every day, it's just not going to happen. We don't have the data to do what you're trying to do. If we are trying to predict ocean temperatures, and we've only ever seen ocean temperatures that go up to say 20 degrees in this particular region, but actually now we're getting values of 30 degrees, you've trained the AI to go up to 20, it's never going to predict 30. It's never seen data of that sort. Other things are like principal components analysis. If you're looking at data of physical processes of a Ferris wheel, and you try to look at this in PCA and it's not analyzed properly, it's going to assume linear relationships that don't match up. We also get that in things like any sort of a data distribution that doesn't match your assumptions. I was seeing a comment, anyone lose my voice? Can people still hear me? I get a thumbs up or some post in the chat.
I can hear you.
Okay, thank you. Okay, next slide, please. So we have to clean our data. We have to have good assumptions on our data that make sense for what we're trying to do. And then, as I said, we need a lot of data. But another common problem is we have way too much data. We have a lot of correlated features or data values that when we throw them into AI, it doesn't really learn much at all. So we also need to do something we call feature selection, where we pick what are the variables of most interest, or what are the variables that are most informative for the AI model. If we give it a lot of correlated variables, just like standard statistical analysis, then what we're going to get is it's going to put maybe 50% of the analysis on this variable, 25 on this one, 25 on this one, but they're all correlated to the same variables. You're not really learning much. One example, we had a project where we were trying to predict what are the conditions going to be in Halifax Harbor at a location where pilots go on to large boats to take them into the harbor. They have a measuring buoy there for this purpose, so they don't need to go out and measure things manually and determine are conditions safe to come into the harbor or not. But sometimes it goes down for maintenance. So we developed an AI prediction model that used another buoy further out towards the ocean to predict the conditions there at Herring Cove in Halifax Harbor in Nova Scotia. In this data, we had things like temperature, maximum wind values, average wind values, wave height, average weight, most significant wave height, etc. A lot of correlated wind and wave and other features. So we had to do a correlation analysis and figure out which of these values were best used in our model, as well as what frequency to sample these at, how to combine them in different buoys, and so on. You can add additional features as well. You can average values, combine values, take historical values. These are all choices in training your AI model. Doing things like DNA analysis, you often have thousands of features and you're trying to predict a small amount of values from a small amount of data. Anyone who's done things like linear analysis knows that's too much data for what you're trying to do. You need to pare it down to those informative values as well. Next slide, please. With that, if we're doing something like saying, is this a cat or a dog, we need to take a lot of time and effort to label those images in the first place. So you have got your data, you've done your data cleaning. If you're doing a project to identify soccer players or objects in a home, you're trying to put AI into a robot, for example, then you need to spend hours and hours painstakingly labeling that data. If you do this in various different ways, like you are getting tired, so you're off a little bit, that's going to greatly impact your results. If you are labeling for example, the same person many, many times, but you don't see different people, then you're going to have good accuracy at finding that specific person, but not others. If you're doing something like fish and you label some fish, but not others, you're not going to be able to find those other fish, or it's going to mislabel them as the ones it's seen before. That said, a lot of work in the AI space lately is on finding ways to avoid this huge manual effort. This can look like you label some data and then you train an AI model that doesn't work very well just yet, use that to suggest additional labeled examples, have someone manually modify those and correct them. We call this human in the loop. Things like ChatGPT, they work based on some sort of data that you don't need to tell it what it is, but it sees so much data and is structured in a way that, for example, next word prediction or other kinds of analysis, that it can learn from large amounts of data without labeling it. So this can be self-supervised, where something like ChatGPT, where it can see what the answer is going to be, or you then do some fine-tuning, or it can be fully unsupervised, where you're learning patterns and correlations in that data. Next slide, please. As I alluded to earlier, often in our real data sets, especially for ocean observing, we're going to have very unbalanced examples. In the upper right, there's an example from us doing some classification of fish species using acoustics and video. And there you can see that, for one, in this river, they were really focused on lamprey. So we have a lot of examples of lamprey, but we also just get uneven distributions of fish species. And so when we trained our AI model, it worked very well on the ones that we had a lot of examples of, but in ones we had one video with largemouth bass, we could not get good performance on that. We see this in lots of different ways in different kinds of data sets. We often talk to people, there's an ocean observing, they really are focused on things like storms or rare events. We don't have much data on those, so it's hard to train AI to work with those. If you are trying to look for something like rare fish, we don't have examples of that. If you want to do, is this something new or interesting? We don't have a lot of examples of that. That makes it very hard to train AI. There are techniques you can do, like collecting more data, use some balancing techniques, you can do augmentation and so on, as you'll see on the next slide. But in general, this is a hard problem. So this idea of augmentation is, let's take our real data and let's do techniques that allow us to leverage that to get more data. In the lower left, we see a picture of a cat. If you often only see it from the side, you're going to struggle if, for example, you have a lot of pictures where the tail or the ears or the paws are missing. To do that, we can rotate our images. We can scale them up or small. We can change the color or the contrast. By applying these sorts of techniques, we can greatly improve performance on different kinds of novel data that we might, if we don't have enough training data, to see those naturally. For example, in that fish sonar analysis, we improved our analysis metric that's called mean average precision, identifying and classifying fish species from these sorts of blurry looking Didson sonar images on the right side here, from 0.41 to 0.73. So it went from really not being usable to not being great, but being something that we could imagine someone using if you do have more data in the future. Next slide, please. That said, even if we are sort of normalizing or using these techniques, if we have poor assumptions and biased data when we're trying to apply our AI, we're going to get biased results. For ocean observing, this can look like you train a model to detect and classify fish species in one region where it's rocky and fairly clear, and you have a battery-powered light. You go somewhere else where it's really muddy and you're looking at natural sunlight, but then sometimes it's nighttime and it's dark. You have different data, you're going to get poor results. And so we need to think about these biases in our data models. Another aspect is, if we're applying these to various different controversial things, like you're trying to do facial recognition on humans, if you train a lot of images on white men, you're going to get good performance on white men and get poor performance on people of color or on women, or if you train everything on, really typically it's white male college students, you're going to get poor performance on the elderly or on children or so on. So that's something that's a huge issue about the ethical application of AI. This needs to be thought of in advance at the beginning of your project, not after the fact when you realize there's a problem. Another big aspect is just determining what these systems are doing can be really hard. We put something in ChatGPT. We saw an example of strawberry having 1 or 2 R's rather than the correct 3. This comes from an assumption in the way these data are encoded into the model. It literally can't tell you because it never sees 3 R's in that. Similarly, we might get models where they say that something is a man sitting on a desk with a laptop. It's just completely wrong. And you can see sort of from a heat map of what it's looking at in that image, it's wrong and had no good data on that. And the second one, it correctly said there's a woman sitting in front of a laptop and it's focusing on the actual woman in that picture. And so, okay, great. And the third one, we can get things that are right, but they're right for the wrong reasons. Here we're saying it's a man holding a tennis racket and it's focusing on the tennis racket, not the man itself. So it could easily have gotten that wrong because it's only focusing and learning based on seeing a tennis racket and saying, oh, I see a tennis racket, it must be a man with a tennis racket. This is an example from our paper looking at bias in these sorts of analyses. So, we need to look more at getting things right for the right reasons, because otherwise we're going to apply them in different contexts and get answers that are going to be wrong in the future, even though when we're training our model, it looks like it's doing really well. Next slide, please. Okay. I'm going to quickly over this one. So another thing is that it takes a lot of time and effort to label data, train a model, especially these larger ones. So we focus a lot on training these big models and then reusing them for other purposes by retraining or fine-tuning with new data from that large model. If we're training a model to identify cats and dogs, we start by taking a pre-trained model on something called ImageNet and then fine-tune it for our specific data. Next slide, please. Now, onto something like ChatGPT. These are the so-called large language models. As I showed you before, though, AI means we take some input of interest, like it could be text, turn it into numbers, apply a bunch of different mathematical operations that have been designed in a way so that they're likely to give us the answers that we want. For something like ChatGPT, it's here is the previous sentence or previous partial sentence, here's the next word, and we train our AI model to predict what is that next word going to be. So that's what it does. That's all it can do. We then fine tune these, people look at these and add new examples to improve them. But even though they look like they are able to generalize to great examples, if you look closely under the hood and under the assumptions into how these are built, then we're going to get things that we call hallucinations or other kinds of things where it's wrong because it doesn't actually know things about what the words mean. It's learned a lot of word associations. This one here is an example I had to actually modify for this slide deck. I used to always use it where I would always ask a ChatGPT to write a sentence where the last word is apple. It would always fail at this terribly because it's never counting what is the last word of my sentence. And it would tend to write something, put apple in there because I asked for apple, but then keep going because that is the way the model worked. I was surprised. I put it in ChatGPT. It actually can do this now. And I did a few times and it works just fine. But then I ask it in the second part here, write a sentence where the second to last word is apple. No, it can't do that. Put in the third last. These methods can't count. My assumption is that this was a common example used a lot. And so then engineers at OpenAI probably put in some more examples where sentences were asked to have a last word that's Apple. So now it can do that task. But it's just papering over the fact that you need to look at the bias and the assumptions and how these are created and not read too much into what they do. They're great tools. They work well for the purposes to which they're designed, but don't always take it at face value. Okay, next slide, please. So that's a whirlwind tour of what is AI, what are some examples of what you can do with AI, and a little bit under the hood of how these things work. You'll see more of those over the next couple of sessions in this workshop. I want to now switch gears and talk a bit about, more specifically, how can AI be used in the ocean sector? This is coming from a set of slides from the organization DeepSense that is run through the Faculty of Computer Science at Dalhousie. Similar goals to what CEOs are trying to do with building bridges, but focus more on the profit sector. So, really great examples, I think, for what CEOs are trying to do in the not-for-profit and other kinds of organization sector. So next slide, please. How can we apply AI for ocean tasks? It applied, again, to a wide range of tasks, things like energy, transportation, transit, recreation, and tourism. I talked a lot about fisheries examples. That's where I tend to work. Military and defense, biology, physical oceanography, or just general autonomous systems. All of these are aspects that these different kinds of AI models can be applied in. Next slide, please. Okay, you just start cycling through this. It's going to do a few different parts. So the way that DeepSense does this, and that I think is similar to what building bridges is going to do through CEOs, first you identify what is the opportunity? Where's the data going to come from? Who are the partners? Who is going to be the AI expert? Who's going to be the domain expert? And you really need all of these people. Scope out a reasonable project. How can we apply AI? What is something that we can realistically do given the budget, the time frame, the data that we have? Do some research, leverage things like student training, master's students and postdocs, leverage funding through things like MyTax Accelerated internships, which is what DeepSense typically uses. Then get a prototype system and see, okay, great, how well does this work? Does it work? Is it a feasible application of AI? Then we operationalize it, work together with the organization so that they can then take it in-house, they can leverage it, put it in their systems, and it continue to grow. And ideally, for DeepSense anyway, the goal is some of these interns are going to be hired by the company and then carry on that work. Next slide, please. We structure this with a lot of support. And again, I think CEOs is going to be similar, where they have those experts that they mentioned that can help you do this kind of work. At DeepSense, we have, we need the domain experts, we need people from the industry company, and they have to be really heavily involved or it's not going to go anywhere. They can't just give us a bunch of data and say, build this. It's not a, a commercial AI development organization, it's a partnership. We have program managers, we have data algorithms leads, we have cloud engineers, data technicians, research faculty like myself, and really this is built on those student interns who are really leading and doing that work. Next slide, please. So now I'm going to give a couple of high-level examples of these areas of where we've applied AI in the past or where we're trying to apply AI. Then I'll go a bit deeper into some specific examples. So we can apply AI to things like structured data, satellite images, underwater cameras. This can be looking at AIS ship tracking data to predict when someone is turning off their AIS transponder. What are they doing in that region? Are they illegally fishing, or was it just a lack of data? Can we predict when ships are going to arrive at certain ports to optimize shipping and plan routes for the shipping industry? Looking at computer vision, remote sensing, satellites. We want to do things like detect and predict corrosion, biofouling, or so on, identify fish species or plankton or things. Lots of different kinds of computer vision tasks. Next slide, please. This can also look like text. We can look at, there's a lot of manual handwritten data in shipping. So can we automate that and analyze that? Social media data, PDFs, textbooks, anything like that, where we can leverage data in different ways. We can look at regression prediction. I mentioned some examples of that previously. A big one is acoustic data. Next slide, please. Big question I often get is, what can you do? And so again, from DeepSense, this is looking at, here is a computer science student. They're doing a 4-month or 8-month internship. Can you go through the words here, please? So this can look like, here's an organization. They need some help at the very beginning. They need to know, how do we get our data ready for machine learning? How do we collect our data? How can we do that? And so that can be a project in and of itself. Second one is, Can we take the data that an organization has? They already have a manual process they're applying. It's time consuming, it's expensive. Can we automate that with the prototype system? Finally, it can be removing barriers, identifying, here's a large organization, here's the data they have, here's multiple different use cases. Where do we start? Can we have extra capacity? Often this looks like, here's a company, they have things they know they want to do, but really they need to have a student and or a researcher who can do these side projects that develop a prototype and justify that business use case to throw resources at it in the future. So these are things you can do in a 4 to 8 month AI project with a couple of people. Think small, think laser focused on here's what I want to get at the end, and you will have something successful. Next slide, please. So now I'm going to go into some specifics of some projects. So take a few seconds to look at this image. And the goal here is identify where is the whale in this aerial image. Okay. Now, I'm sure many of you are looking at that darker blob there in the middle, but if we advance to the next part of this slide, you'll see that it's actually in the lower right, and that in the middle is the ship that's observing the whale. So often it can be very non-trivial to do this sort of work. As I said before too, we need to label data in this way. You need experts. Otherwise, we're going to get wrong results. Next slide, please. And so, these images can be very varied. They can be difficult to work with. You need to go through all of them to label all of them consistently. And it's a lot of work to do that task. Next slide, please. Another one, which I think you'll actually be hearing about in one of the future sessions the next couple of weeks from the COO of Glass Ocean, Sue Malloy, so I won't be saying too much about that, is looking at vessel efficiency. So I'll really quickly go through this one. Can you advance twice, please? We can look at things like boats moving around and try to predict what is the fuel usage of these vessels. Glass Ocean has developed a measuring system to do this work. It's not as simple as it is for large vessels or for cars, but it's really key to do this work, even on small vessels, to help decarbonize and optimize efficiency. We can also do things we call anomaly detection. That's where we develop an AI system, we have it going, and if we see that we predict something and it's very different than what's actually happening, either there's a problem with our model or the conditions are different. This could be a way to identify, oh wait, this vessel actually has some engine trouble. So we can see that it's using much more fuel than we predict, not because there's an error with our model, but because there's an error with the conditions. So in this case, it was an engine that was leaking fuel. Next slide, please. The third example I'm going to give is on using AI to classify and track fish species in hydropower. This is a project together with Nova Sea and Nova Scotia Power, where they're instrumenting these turbines at various different rivers in Nova Scotia. This started with a research project with DeepSense and with Dalhousie University to develop a proof of concept, and now they're scaling this up massively to, I think, 15 different rivers. So they put cameras at these fish ladders. They developed some AI systems to automatically count fish. Previously, this would be manual, painstaking work done by student interns, and only for a small portion of the season, only during the day, getting really limited data. And now they're able to get much more insight into these by getting data all the time, doing a lot of work on the company side to develop apps and visualization techniques and so on to analyze these systems with something they call Hydro AI, funded by Canada's Ocean Supercluster. So last thing I want to show, if it will run for us, is just a quick video from Nova Sea showing kind of what this looks like. And you'll see it's a lot of what I talked about with that AI. It's drawing boxes around fish and counting those fish. Okay, so if this can't play, then I will just describe it, but we'll see if the video plays. No? Okay. But what you would see is here's some images of fish swimming through this fish ladder, and we developed AI that will, 1, draw boxes around those fish, 2, identify what species they are. In this case, it was in the Gaspereau River, so they're mostly Gaspereau, and 3, add tracking numbers to those. I didn't talk about tracking, but that's another part of AI where, that is it a cat, is it a dog, is for each image, but now you have a set of images in a video, you need to follow those along with AI that is going to say, this is the same fish, so we don't double count. So a lot of fun work. And Nova Sea has hired 3 of our student interns over the course of our last 3 years together working with them on this project. So thank you very much. If we have time, I'd be happy to take a few questions. I see lots of interest in the chat.
Yes, absolutely. Thank you so much, Chris, for your insights. We did get a couple questions for you if you have a couple minutes to answer. First, from Hatem, how can I choose the AI model or technique that best suits a specific situation?
So this goes back to that beginning piece of what I said, that process where we apply with deep sense. It's actually a hard problem, and it's really crucial. Typically what we do is we look at the problem you're trying to solve. We look for similar work that has tried to solve that problem before. Then we look at a few different candidate AI models, and typically you're not going to be able to say this is the best approach right away. You have to build that prototype system, try a limited amount of data with a couple different models, and then focus on the one that performed best, optimize it, get a full prototype, and then maybe consider, now that I have more data, I've learned more about this problem, what should I do to optimize it? So there's no one solution, but it looks like, do some reading, do some searching, see who has solved something similar.
Great advice. And then a quick follow-up. Shall we reduce data dimensions before applying the AI model?
Again, it varies. Look at what people have done before. But for example, in that buoy prediction problem, we really had to reduce the dimensions. So AI is often kind of thought of as a black box where you just throw a bunch of numbers at it. Here are your output examples and you get what you want. But take some time to think, do you have a data such that if you gave this to an expert in this area, they could figure something out? It doesn't apply to all problems, but for a lot of these ones, again, like fish classification, you really need to know that with the data you're given, it makes sense in a way that it can solve that problem. So if you have a lot of different data to the point where you get confused about which data you have, or there's lots of correlations, then yes, you probably want to reduce it. That said, I always like to say, get something that works, not something that's perfect for AI. So get something that works, and then look at where you are. And if it's not good enough, then maybe rethink that and add some of that data back in.
Excellent. Next question from Dwight. What are some good examples of using crowds or citizen scientists to train models for marine applications?
So there aren't a lot of these that much yet for marine applications. I was recently at the American Fisheries Society annual meeting in Hawaii, and there they have a great citizen science program where they have divers. They dive down, they have cameras, and they give them a task where it's, here are a couple of different fish we want you to try to find. Take a picture of those. They've got stereo cameras so they can measure how large the fish are. And they made it sort of a fun game to go out and find these fish. So that's one. I know that in California, the Monterey Bay research group, they have developed a mobile app where they call it Fathomverse, where they show you examples of marine images and they make it a game to annotate those and say, which fish species are those? So those are a couple. But really, I've been looking for some, and there's not as many examples of citizen science in the marine sector just yet. So this is really something that's starting to really grow. But if you look in the terrestrial sector, there's tons, right? You can get an app that will help you identify what plants you see, and you can improve them if it's wrong, or birds, or so on. And we're only just starting to get these in the marine space.
Excellent. And then one final question before we have to move on. Do you have any resources that list the various AI models that are available for end users?
I don't. This is something I would love to create, or maybe it's something that CUS might be interested in creating as part of that work they were talking about in documentation. I started to do it a long time ago. We first started Deep Sense about 5 years ago. Then we got really more focused into each individual application of AI. And what we found is that every problem is very different. There's a lot of commonalities, but I think now, as more and more people are starting to use it for ocean applications, we're starting to get onto a more standard set of these are the kinds of things we can solve. So I think we're probably getting close to being able to do that. I've seen some examples of that in other sectors. For example, Climate Change AI is an organization that is doing this for climate-related problems in general. They've got a couple of ocean examples. And so I think it's something that hopefully might come out of this Building Bridges opportunity.
Yes,
so that's
absolutely.
the first steps.
Well, thank you so much, Chris, for your time and for your wisdom. We do unfortunately have to move on to the next presentation here, but if you do have any other questions for Chris, hopefully we can circle back at the end, or of course we can try and answer those in the chat. But for now, we are going to move on to 2 lightning talks from researchers at Dalhousie, both working on the Building Bridges project. First is Jay Kumar, who is our AI developer, and he will be sharing his current work on AI for data management.
Great, thanks. So again, yeah, I'm working for as a AI developer in the CUs. So I'll be checking about what I have, like AI for the data management, what I have done, what I have come so far. So next slide, please. I'll just go through the bird eye view, how data management pipeline or workflow goes. And currently we have, as discussed, that we have a variety of data. So let's assume that we have a contributors or partners who are sharing the data from satellites, from buoys, or from other kind of stuff, from other kind of sources. So what they do, they actually transfer the data, and they also provide the metadata, the data information about the data. What is done with the data and metadata is again forward to the next process of data processing, which data management does. We have a set of tasks, we have a set of scripts to filter out the data, or if there is any kind of a necessary operation has to be done in the data. And in the next step, the data is again published on any cloud server, on a data server, and with the catalog, and that can be accessible for a public use. By using the published data, by interacting with the published data tool, user can download like the set of data of the, or set or subset of the data what they want specifically. Each of the step of this data management has to be there are many possibilities to apply AI, but right now with the limited time, I have started focusing on these three things, like these two things specifically, trying to focus and trying to adopt how AI can be possibly integrate to enhance more manual tasks and to enhance user experience. So first one, I'm going to focus on how data processing is, like how can we integrate the data processing and enable AI to improve that process. So in the next slide, let's say we have a contributor and which gives us the data. It provides us the data over the time, because we have a couple of contributors or partners who are actually publishing the data over the time. So let's say if they are in an iterative process, they are providing the data and the metadata. So can you please do the next one? Yeah, click one. Yeah, thanks. So they provide the data and the metadata and information about the data. So each metadata and data comes and processed through a validation process where I mentioned there are a set of tasks, there is a set of filtration, or there's a set of validation which comes across this metadata and data, and then these metadata is published through the CKN data like catalog services. And as Alexi mentioned about the data is published to the data server, which is RDAP. Here's what, as I was investigating what things has to be, as one of the points mentioned, Chris mentioned, that how to eliminate the human error, or how to actually automate the task, the manual task, and do automation. So what I found, when there is an iterative process and when new data from the same collaborator comes, there might be chances that new variables are introduced, or the variable names or attribute names have been changed. For that one, data manager has to dig out what is the actual history and check out the repository by themselves and try to predict what should be this variable. What here the AI comes, actually that actually takes more of their efforts to detect that one. So that's what I have figured out, that there is a need of AI. There's a predictive tool, needs to be a probabilistic or predictive tool, which can automatically detect this kind of variable or attribute name. So in the next slide, I'll just focus on the publishing task, that how to enhance the user experience with the AI. So on the RDAP portal or in the catalog portal, there's an operation of searchability and interoperability. So usually when we go, as Chris mentioned, there is, if we are talking about movie recommendation, if we are actually searching a movie or we have a similar kind of interest. So Same with this data, same with our portal. How can we develop a data set recommendation if we want to enhance the user experience of like searchability with the variety of terms? It's not necessary that a particular population of users is coming like a researcher. There are different type of people, heterogeneous type of users can come to the platform and use the data. And my focus is to build a data recommendation system which enables or recommends the data in terms of various dimensions, including like geographical, temporal, or other variable stuff. And the backbone of that thing is how can I link the data set and group the data sets and with different properties anyway. Thanks, Doug. I have summarized my work in a very precise way. Thanks again. Thanks, everybody.
Excellent. Thank you so much, Jay. Next up is Shayla Fitzsimmons, who will be highlighting the work being done on data interpolation using AI.
All right. So I am presenting this on behalf of James Monroe, who is actually doing this work for us, but unfortunately he wasn't able to join us today. So one of the components of building bridges is looking at the data. So ocean observation data, a lot of the time it's not uniform in time. When you have a time series, you might have gaps, or you might have data that's removed because it doesn't meet the quality control requirements. But for things like artificial intelligence, you often need data that is uniform, right? You need a long time series that has data collected, for example, every 10 minutes. And so to address this, you often need to do some combination of gap filling or data interpolation or error correction. So as a motivating example, we're really looking at the water quality data set collected by the Center for Marine Applied Research here in Nova Scotia. And specifically the sensor string data they've collected from around the coast of Nova Scotia, which is a multi-year data set that collects temperature and dissolved oxygen data. So the plots on the screen here, the one in the middle is taken from the Spry Bay Station in Halifax County. For temperature, you can see it looks pretty good, right? There's not a lot of gaps. It looks like it goes up and down in a fairly predictable manner. But if you look at the one below that, the dissolved oxygen, there's a lot of gaps, and also it's clipped. Anything above 120% saturation or below 85% saturation have been removed because they didn't meet the data quality requirements. So there's quite a lot of gaps. So there's kind of two aspects to that. This data from 2019, it appears as if it was configured to collect data at high frequency for a short period and then go a longer period, a few hours, without collecting any data at all. This was presumably to preserve memory storage or battery life, but it does make it a little bit more difficult to use that data when you need uniform sampling. So one solution that you could do, but isn't necessarily recommended, is to downsample the entire record so that you remove all the data in between a certain time period, right? So if you have data every 10 minutes for a period and every hour for another period, you would remove it so you only have a data point every hour. We don't actually recommend this because that eliminates all the rich high frequency information that could be really useful in your analysis. So what we're looking at instead, is it reasonable to gap fill for this kind of intermittent sampling? The other thing we're looking at that I had mentioned on the first slide was the removal of data from QA/QC processes. So in this graph, the light green is the actual data that was observations that were collected. The dark green is the data that passed QA/QC. So you can see the straight lines are actually filling in gaps where data was removed. So there's quite a few gaps in here. So for example, is there a systemic error in the data that was removed with QA/QC? And can we back out that systemic error to get good data from the bad data? And this is, for example, assuming that maybe instrument drift can be calibrated over time for a particular data set or instrument type. So our next steps for this particular component of building bridges is to take what we know is good data and then to create test and training data sets out of that. So to purposely, for example, remove certain data points and artificially generate gaps. And then once they're built, use them to explore a number of different machine learning algorithms, including linear regression, support vector regression, random forests, multi-layer perceptron, and recurrent neural networks. Assess how they work. And from that, consider, is this a reasonable solution to help fill in gaps in data or to improve the quality of ocean data? And can that be then used more broadly and on more different data sets and for more different data types? So we're still fairly early stages with this, but I think there's a lot of really exciting applications and we're really excited to see where it goes.
Excellent. Thank you so much, Alexi. Oh my gosh. Thank you, Shayla. We will now open the floor to questions from the audience for these last couple minutes here. If you have any questions or comments to any of the panelists that you heard from today, please send them in the chat. You can also reach out to us later on social media. Also, you can email info@seussatlantic.ca. But we don't see anything coming through. So why don't we go to our concluding slide, Shayla? Basically just wanted to thank you for coming. Thank you to our panelists for joining us today, especially Chris for taking the time out of your day. If you are interested in attending the next sessions of this workshop, Session 2, Preparing for AI, will be on the 13th of November, which is next Wednesday. And then Session 3, which will be all about use cases and case studies for AI, which will be on Thursday, the 21st of November. And yeah, like I said, if you have any other questions for us later, if you want to stay connected, please feel free to reach out to us. You can find us on social media, Facebook, Twitter, and our email as well. You can also find us at seuss.ca or seussatlantic.ca is our specific regional address. And lastly, these presentations are being recorded and you can find them on YouTube after the fact. So thank you everybody for joining us. Really appreciate your time today.